Hi there, welcome to our Curves&Surfaces group project. Presenting to you today will be myself, Zainab,
Tarveen,
Nadira, and Emily.
So now we will start off with plane curves.
So consider the parameterized curve gamma in the plane which depends on t. The plot of the curve is shown below. For a curve gamma, the tangent of the curve is defined as gamma prime of t.
Hi there, welcome to our Curves&Surfaces group project. Presenting to you today will be myself, Zainab,
Tarveen,
Nadira, and Emily.
So now we will start off with plane curves.
So consider the parameterized curve gamma in the plane which depends on t. The plot of the curve is shown below. For a curve gamma, the tangent of the curve is defined as gamma prime of t. So the norm of gamma prime of t will be the norm or the length of the tangent. The arc length function of the curve is given by the integral of the length of the tangent with respect to u between t to t0, where t0 is a fixed point in the domain alpha beta. By definition, a curve gamma has unit speed if the length of the tangent is equal to 1 for all t in the domain, whereas if the length is not equal to 0 for all t, then the curve is called regular. So the differential of the arc length function is the speed of the curve. In our case, the curve is not unit speed. It is, however, regular for all t. There is a theorem that states that a curve gamma has a reparameterization by unit speed if and only if gamma is regular. This means that we can find a new curve of our original gamma such that the new curve has unit speed. We reparameterize a regular curve by carrying out these 4 steps. First, you check if the curve is indeed regular, then compute the arc length function, then find the inverse of the arc length function, and this will be our reparameterization map phi. Our new curve is then defined as gamma of phi of t. So theoretically, we can carry out these 4 steps and reparameterize our original gamma. However, the curve has an elliptic integral, so the reparameterization will be difficult to calculate. Have you ever wondered how much a curve curves? There is a measurement of this, and it is called the curvature of the curve. If the curvature of a curve is equal to 0, then the curve is just a straight line. If our curve is unit speed, then the curvature is simply the norm of gamma double prime, that is the norm of tangent prime. If our curve is regular instead, then we have this formula over here. For our curve, since it is regular, we find the curvature by using the formula, and we found that it is not constant. There is also another type of curvature which is defined only for the plane curves, and that is the sine curvature. It measures the rate at which the tangent vector rotates. If it is positive, then the curve is moving counterclockwise, or else otherwise. We have the formula for the sine curvature of a planar unit speed curve shown on the slide. It is just the curvature of a planar unit speed curve without the determinant on top. We can find the sine curvature of a regular curve by first reparameterizing the curve to unit speed, and then find the sine curvature using the formula given. However, for our curve, as mentioned earlier, it has an unknown unit speed reparameterization because of the elliptic integral. So it will be hard for us to find the sine curvature of our curve.
Now we'll define what a space curve is. We've seen what a plane curve is, so a space curve is just simply the projection of a plane curve in R3. For example, the space curve is the equation given on the screen, and we can visualize our space curve by the clip also. And as you can see, it would be very hard to model. Let's now look at surfaces. The parameterization of a surface is given by x, u, v. In fact, our space curve lies on the surface. By simply substituting u equals 1 and b equals t into the parameterization of the surface, we get our space curve equation. This surface is actually very important. It's a Hellenberg surface.
Our surface is Hellenberg's minimal surface. It's a non-orientable minimal surface named after a famous German mathematician from the 1870s. Up until 1981, the Hellenberg surface was the only known surface of its kind. Now let's explore some of the interesting properties that it holds. Our surface is non-orientable, and an easy way to understand this is using the famous Mobius strip as an example. This is a simple surface that can be created by linking the ends of a strip of paper with a twist in the middle, as shown in the video now. So if we start at one point on the Mobius strip and face in one direction, as seen by the arrows, and move all the way around the surface facing the same direction, we shall eventually see, when we get to the end, that we're now not facing in the same direction that we started with, as the arrows are pointing in separate directions. Hence we haven't kept our orientation. So this is the same for our surface, it is just more complicated to show. As our surface is non-orientable, we cannot find a global gas map for our surface which holds for all points on the surface. This would be a map that would take the points on the surface in R cubed to the unit sphere, represented by s squared. We can, however, calculate a local Gauss map for points lying on the surface, meaning that we can do further calculations to find out more about the surface. This will be discussed later. A minimal surface has a mean curvature of 0, and Zainab will discuss how to calculate this later. A surface is minimal if it minimises the surface area for given boundary conditions. There is a lot of history behind minimal surfaces, and many famous mathematicians have been involved in their understanding during the 19th and 20th century. In 1768, Lagrange was the first who discovered equations to prove that a surface was minimal, and then later, another famous mathematician discovered that the conditions of a minimal surface led to the conditions of the mean curvature being 0, which is something we still use today. A pretty awesome way to show that a surface is minimal is using the soap film method as seen in the video. This method involves creating a surface by dipping a wire frame into a soap solution, forming a soap film, which is the minimal surface whose boundary is the wire frame. This works as the bubbles will naturally join the boundary of the curve in the smallest area possible. We could use this for our surface, but we would need to restrict the domain so that there were no self-intersections, allowing the soap film method to work. Hence we have determined it is minimal by calculating the mean curvature and finding it to be 0.
So, another way to show if our surface is minimal is to calculate the curvatures. The curvatures that we will be calculating will help determine the characteristics of the surface. So, how can we calculate these curvatures? Well, we have to calculate the first and second fundamental forms. These calculations will then help us calculate the Gaussian and mean curvature. With our parametrized surface, we can calculate the coefficients of the first and second fundamental form. But before we get to the nitty-gritty part, what do these forms show? The first fundamental form enables us to calculate the lengths of curves on the surface, areas of regions on the surface, and the angles on the surface. The second fundamental form relates to how curved the surface is. We have cheated a little bit and we're not going to bore you with these bad boy calculations. We'll just use A as a matrix to obtain the principal curvatures. The principal curvatures are used to calculate the Gaussian and mean curvature. So, we calculated the mean curvature using the principal curvatures, which will look pretty at first, but then simplify to equal 0, hence why a surface is minimal. If h didn't equal 0, but was a constant, then the surface would be a constant mean curvature surface. With the principal curvatures, we calculated the Gaussian curvature. We got this nasty looking thing here. We would have had a k surface when k equals c, where c is a positive real constant, but, however, as our surface does not have a constant curvature, because it depends on the parameters u and v, so by changing u and v, the Gaussian curvature will be different for each point that lies on the surface. We hope you have enjoyed our video on curves and surfaces and mostly our voices. Here's a quick look at our parametrized surface. So, quickly to summarize, we have gained a clear understanding of plane curves, space curves, and surfaces, and how through different calculations we can understand each topic more. Thank you, and goodbye until next time.